All right, welcome to The Explainer. Today, we're going to pull back the curtain on a force that powers, well, pretty much everything in our modern world, electricity. It's totally invisible, it's everywhere, and by the end of this, you are going to understand exactly how it works. So let's jump right in.
So to get started, just think about something you probably do every single day. You plug in your phone. You see the little battery icon fill up, but what's actually happening inside that cable? What's that invisible river that's bringing your phone back to life? That's the big question we're going to tackle today.
To really get it, we need to meet the three stars of our show. You can think of them as the main characters in the whole story of electricity. You've got current, potential difference, and resistance. If you can wrap your head around these three, you've pretty much got the whole picture.
Now, since we can't actually see electrons with our own eyes, probably the best way to visualize all of this is with a really simple analogy. Just picture water flowing through a pipe. The physics are actually surprisingly similar, and it's a fantastic way to get a feel for the concepts we're about to cover.
Okay, first up is current, which we represent with the letter I. This is just how much electric charge is flowing past a certain point every second. In our water analogy, it's how much water is gushing through the pipe, and we measure current in something called an ampere, or you've probably heard it called an amp.
But what makes that current flow to begin with? It doesn't just move on its own. That's where potential difference comes in, which, we all just call voltage. It's the push. It's the electrical pressure that gets those electrons moving down the wire. Just like water pressure in a pipe, more voltage means a stronger push. And it's measured in, you guessed it, volts. And that brings us to our third player, resistance, or R. You see, every material out there puts up a bit of a fight against the flow of electricity. It's like electrical friction. In our analogy, this would be like a skinny part of the pipe that squeezes the flow and makes it harder for the water to get through. We measure resistance in a unit called the ohm.
So we've met our three key players: current, voltage, and resistance. The thing is, they don't just exist on their own. They're all connected in this really specific, really elegant relationship that basically forms the golden rule of electronics.
So the big question is, what is that relationship, right? If you crank up the voltage, what happens to the current? If you add more resistance, how does that affect the flow? Well, it turns out there's this beautifully simple formula that ties it all together.
And here it is. This little thing is Ohm's law. Voltage equals current times resistance. V equals I times R. It might look simple, but this equation is the foundation for pretty much all circuit design. It tells us that the push, the voltage, is always equal to the flow, the current, multiplied by the opposition, the resistance.
And this right here really shows Ohm's law at work. Check it out. The voltage is staying the same, right? It's constant at 12 volts. But as we increase the resistance, we're going from 2 ohms up to 4, then up to 6. Look what happens to the current. It gets cut in half, from 6 amps down to 3 and then down to 2. So more resistance means less current can push through. It's a perfect relationship.
Okay, now that we understand the basic rule book, let's see how we can actually arrange things in a circuit. Because it turns out the way you wire stuff together completely changes how our electric trio acts. You can give the current just one path to follow, or you can give it a bunch of different options.
The two main ways to build a circuit are called series and parallel. Think of a series circuit like old-school holiday lights, where everything is connected in one single loop. But in a parallel circuit, the components are on their own separate branches, kind of like the lanes on a highway, giving the current multiple paths it can take.
So the most important thing to remember about a series circuit is that there's only one road. That means the amount of current flowing through the very first component is the exact same amount of current flowing through the very last one. And the total resistance? Super easy. You just add up all the individual resistances.
Now, a parallel circuit, it's a whole different beast. Here, the voltage across every single branch stays the same. The total current is just all the currents from the separate branches added together. And here's the kind of weird part. Adding more paths in parallel actually lowers the total resistance of the circuit. It's like opening more checkout lanes at a store. It makes it easier for the overall flow of traffic.
So why should you care about any of this? Well, this quote really nails it. Your house is wired up in parallel. And that's super important because it makes sure every outlet gets the same amount of voltage. And it means that if one of your light bulbs burns out, it doesn't kill the whole circuit. All the other lights on their own separate branches just stay on. Pretty smart, huh?
We've been talking about resistance as this property of a circuit, but what is it about the wire itself that determines how much resistance it has? You know, why is copper wire so great at conducting electricity, but the rubber coating around it is so bad at it? Let's zoom in from the whole circuit down to the material itself.
The secret is in a property called resistivity. You can think of it as a material's electrical fingerprint. It's a built-in value, just like its density or its color, that tells you exactly how much that material naturally fights against the flow of electricity. Copper has a super low resistivity, which makes it a great conductor. Rubber has a crazy high resistivity, making it a fantastic insulator.
But it's not just about the material. The actual shape of the wire matters too. The resistance of a wire is directly proportional to its length. So a longer wire has more resistance. And it's inversely proportional to its area, which just means a thicker wire has less resistance because it's giving the current a bigger, wider path to flow through. Makes sense, right?
So we've pretty much established that all materials have some resistance. But what if they didn't? What if you could have a material with absolutely, positively zero opposition to the flow of current? Well, this isn't science fiction. It's a real and amazing phenomenon called superconductivity.
The story here is pretty cool. It starts way back in 1908, when a physicist named Heike Onnes finally figured out how to turn helium into a liquid, which let him get things colder than ever before. Then, just a few years later, he made an incredible discovery. When he cooled mercury down with that liquid helium, its electrical resistance didn't just get low, it vanished completely. It took scientists another 50 years to even figure out a theory to explain it.
Now, to get this to happen, you have to get things incredibly cold. I mean, we are talking about temperatures near absolute zero, which is 0 on the Kelvin scale. That is the coldest temperature that's theoretically possible anywhere in the universe. It's the point where atoms basically stop moving. So what's the big deal about zero resistance? Well, get this. If you start an electric current flowing in a closed loop of superconducting wire, that current will flow forever. There's nothing to slow it down, so it just keeps on going. This wild property lets us build unbelievably powerful magnets, which we actually use today in things like superfast maglev trains and the MRI machines you find in hospitals. The catch is, all the superconductors we have today need that extreme cold, which is really expensive and hard to maintain. So that leads us to our final question, the big one. The holy grail of physics right now is the search for a material that can do this at room temperature. So just think, if we found one, how would that change our world? From power grids with zero energy loss to technologies we can't even imagine yet, the possibilities are just staggering. Something to think about. Thanks for joining us on The Explainer.